So essentials first, they're carried out in a similar way to an acid-base titration. One species is reduced and another is oxidized. You don't always need an indicator, and that's because one of the chemicals is often coloured because it's a transition element, and as it reacts it changes colour, or the colour fades away, as you'll see when we look at the example. So some examples include Manganate 7 titrations, ethane dioate and Dichromate 6 titrations. So we'll look at the procedure for Manganate 7 titration. So the standard solution of KMnO4 is added to the burette. We use a pipette to measure a volume of the solution under analysis and transfer that to a conical flask. We add an excess of dilute sulfuric acid to the conical flask to provide the acidic conditions for the reaction. We carry out a trial titration. So in the case of KMnO4, as that's added from the burette, it oxidizes the solution under analysis. Now that's often iron 2 plus going to iron 3 plus, but not always. As the KMnO4 reacts, the ions, the MnO4 minus ions, are reduced to Mn2 plus and they lose their purple colour. Once all the chemical under analysis has been oxidized, so in other words, once all that Fe2 plus is gone, the KMnO4 has got nothing left to react with, so the next drop of that stays purple after swirling. So the colour change would be colourless to purple. You record the titra and then you repeat the titra until you get two concordant results. So not including the trial, you need two results within 0.1 cm cubed of each other. And finally, here's the equation for that reaction. Now you don't have to memorise these, you'll be given enough information in the question to either work it out or you'll be given the equation directly. So we'll look at a couple of examples now. The first one I've chosen is an acidified Manganate 7 titration. So if you want to have a read through the information on the screen now and have a go at the question and then play on when you're ready for the answer. Now often with these questions there's a bit of a minefield of information you've got to get your head around, and I always advise my students to draw little diagrams so they can actually visualise what's happening. So we'll do that first. So they've taken 2.5 grams of a metal which contains some iron and dropped it in some sulfuric acid. And what that's doing is it's turning the iron atoms in the metal into Fe2 plus ions. So you can see there's a 1-to-1 ratio there between those two. That's important. So at the end of that reaction you've got aqueous Fe2 plus ions now in that beaker and those H plus ions. That's then poured into your volumetric flask. Remember it's 250 cm cubed. So essentially the moles of Fe2 plus in this beaker are the same as the moles in here, because we literally just poured the contents of that in there and filled it up with distilled water. And then 25 cm cubed is taken out of this volumetric flask, put into your conical flask, and then the titration is carried out with that purple KMnO4. So if you're wanting to work out the percentage of iron in the metal, you're going to need to know the moles of iron in the metal and then the mass of iron in the metal, and then compare it to that 2.5 grams and express it as a percentage. So that's what we're heading for. It's always a good idea if you know what you're heading for. So the first thing we can do is calculate the moles of MnO4 minus in that average titra. So there's the answer for that there, concentration times volume in dm cubed. Mole ratio gives us the moles of Fe2 plus in the 25 cm cubed used in the titration, so that's that there. In the 250 cm cubed will be 10 times more, so we'll just multiply that by 10. Remember we said the moles in here are the same as the moles in there. So the moles of iron will be the same as well because of this 1-to-1 ratio here. And so now we know the moles of iron in the metal, we can turn that into grams by multiplying by the MR. So the metal actually contains 1.245 grams of Fe, so as a percentage, to three significant figures, it's 49.8. So The second one I've chosen is an acidified Dichromate 6 example. So again, if you want to have a go at that, pause the video and then play on when you're ready. So again, in terms of pictures, they've taken 7.49 grams of the hydrated FeSO4, and we don't know what the XH2O is. That's the whole point of the question. So that's dissolved into some water, and so literally it's just going to dissolve, and the FeSO4 is going to turn into aqueous Fe2+ and aqueous sulfate ions, and the X water is just going to become part of the water in the whole solution. So it's acidified, and then we've got this beaker of aqueous Fe2+ ions and H+ ions. That's then poured into the 250 cm3 volumetric flask, 25 cm3 taken out for the titration. So in terms of what do we need to calculate, well, we need to know the moles of FeSO4.XH2O in the 7.49 grams so we can work out the MR. And then once we know that, we can subtract away what we do know about the formula, and we're left with the mass of the X waters. So very similar calculation to before at the start. So the moles of Dichromate 6 used in the average titra, concentration times volume. Mole ratio now is 1 to 6, so we multiply the moles by 6 to get the Fe2+ in the 25 cm3. Multiply by 10 to scale it up to what was in the 250 cm3. Those moles are the same as those moles, which are the same as those moles. So we've got that many moles of FeSO4.XH2O. So the MR must be the mass divided by those moles, so we get an MR of 281.9. And now we're going to subtract away the MR that we do know, so FeSO4 has an MR of 151.9, so if you take that away, we get 130 for the X waters, and then if we divide by 18, the MR of water, we've got 7.22 moles of water in the salt, so to the nearest whole number, X is 7.